this problem, we're asked to calculate the change in energy per mole. Now, one of the things that is not clear is per mole of what? It is actually per mole of this product, the helium-3. So when we are calculating the change in energy for a nuclear reaction, we're going to use E equals mc squared. So we're going to determine the change in mass from our product side to our reactant side. Remember, a delta is always the final minus the initial. So here's a table with the masses of my deuterium isotopes as well as my helium-3 and the neutron. So I'm going to use these to calculate the difference in mass between my product and my reactant side. So my product side, when I add up my helium-3 and my neutron mass, I get 4.02469 AMU. And then when I multiply the mass of a deuterium isotope by 2, I get 4.02820 AMU. So our change in mass as I go from reactant to product is negative 0.00351 AMU. And this is how much mass, the change in mass per helium-3 isotope. Now it's a negative because I'm losing mass, but that mass is being transformed to energy through this relationship right here. So to be able to use this relationship equals mc squared, I've got to get the right units for my mass. And I was also asked to calculate energy per mole. And what I calculated was the change in mass per helium isotope. So I've got to convert the per isotope to per mole and the AMU to kilogram. So there are 6.022 times 10 to the 23 AMU in 1 gram. There are 1,000 grams in 1 kilogram. And there's 6.022 times 10 to the 23 isotopes in a mole. So we end up with an overall value of negative 3.5 times 10 to the minus 6 kilograms per mole. So as I go from reactant to product side, this is the amount of mass that is being transferred to energy. So I square the speed of light, multiply it by the delta M in units of kilogram, and I get negative 3.15 times 10 to the 11th joules per mole. Be sure to include this negative side in the energy when you put the answer in.